Like this. Where is Abu Bakr today? Afan?
Yeah, I have no idea. And I think nobody else is here, just me and Javeria Shaheed.
Yes. I don't know why. What happened? Did they not receive the link? Did you receive the link?
I did
Yes,
at
yes.
7:02.
I don't know. How could 10 people be absent at once? I have no idea. What a coincidence this is. Alright. Never mind. We're gonna go to the next then. In any case.
Is today even a regular class time?
Out जाना है आपको side से. This EATC. Yes. All right. Never mind. So now today, just for your information, I just want to tell you that there are different transitions that can happen within the hydrogen atom. You can draw these transitions, and then we're going to go forward. This is called basically electron transitions for hydrogen atom. Basically, we are at the ground state. Then,
Isn't it the same thing?
yeah, same thing. It's kind of it is something I want to tell you about this. I want to make seven. So usually, when you're looking at the energy levels of hydrogen, you have jumps. Like if the jumps are made between 7 to 4, like this, or 6 to 4, anything up till 4. Okay, this is called the bracket series, just a name. And then if the jumps are made from 7 to 3, like these are called the Paschen series. And then the jumps which are much higher than this, 7 to 2, these are called Balmer series. And then if you have the longest possible jumps, like this is basically called the Lyman series. Now for Lyman series, just want to tell you, in this one, you have, whenever this happens, there's a typical microwaves are released here. sometimes radio waves as well. In this one, you have typically infrared series waves. In this one, you will have visible light, and in this one, you will have ultraviolet released from the hydrogen. Is it clear? Now, all these releases basically form us a spectrum because all range of wavelengths come in. So I'm gonna just write few definitions here. First of all, let's look at spectra. Spectra is defined as a of range of frequencies that are emitted or absorbed, and then we have continuous spectra, where continuous spectra is an emission spectra that occurs when a material is heated until it is white hot. Okay. So then what happens is a continuous spectrum a continuous spectrum has analogous transitions in a range of frequencies with no step variations or sudden changes. All right, kids. So it's basically a very smooth transition system. And why this is called an emission spectra? Because it is called an emission spectrum because gas is excited and so light is radiated. I will show you how it looks as well. You can write this down and then we're going to go forward. All right, kids, when you're done, let me know, okay? All right, it's now we're going to go to the next, which is basically the line spectra. In a line spectra, you guys need to remember, line spectra is an emission spectrum, a spectra of a number of discrete, sharp frequencies and wavelengths of bright lines that corresponds to the quantized energy gaps, and that is delta E equals to hc upon lambda, like that. So I'm going to tell you what these energy gaps mean. So basically, when suppose that in an experiment we want to basically investigate or see the emission line spectra of hydrogen. So what happens? Let's have a look. Now, typically we want to have an excited gas. Generally, we provide some sort of electrical energy to it, so that we can have an excited hydrogen gas. Yes. And then we basically let it pass through a grating because we want it to diffract. Nicely draw this. Like that. And through the grating, we want it to go through a prism. And then through the prism, in front of it, we put a screen so that we can see what's happening there. So basically, this would be the grating. This would be the prism. So the light from it, the photons that are released, passes through the grating. Then it moves through the prism. And on that, we generally get four different colors: violet, and then blue, and then we have cyan. Wait, that color, na? I have
Looks like turquoise, basically bright green with a tinge
turquoise.
of blue.
Yeah, yeah.
That's cyan.
It's sort of this sort of color. Okay,
Yes.
it's not very visible though. Let me just color it more. And then we have let me put it a bit darker. because then it would be sort of this color. Yes. And then you have red that comes out. Okay. Now only these four colors are emitted and nothing else. So when you see the screen of the spectra, everything is black except for the four colors, which are primarily violet, and then blue, and then we have cyan, and then we have red. And obviously, each color that comes out has its own wavelength. Like violet will have 410. All of these are nanometers. Blue will be around 434. This will be, let me just write the numbers only, 410, 432, 486, and red is around 650. So we have all of these in nanometers that come out. Nothing else. Everything is like pitch black. Everything else. All right, kids. These lines that form are basically these lines are bright, discrete, sharp, and unique to every gas, like that. All right, kids. Do you understand that? Abu Bakr, very bad. Very, very bad. If you can draw. Otherwise, you can write. Okay. Because if you don't have colors, it's fine. Because for some reason, all of you people have decided to take a day off today. Why?
Wasn't there a match today? Oh wait, no, that was India and New Zealand. Pakistan's been out. Never mind. Yes, Bakar, you were also late today. 35 minutes.
No, Abu Bakr, no. Very bad. Okay, now, so Mr. Bakar, we have done that we excite the gas. Exciting gas would release some photons, and these photons from the hydrogen gas are released. Only four of these colors appear, and these lines are formed of sharp, discrete frequencies or wavelength. Why? Because they tell you about the structure of hydrogen gas inside, like that. All right, kids, write it down, please. Please write this. This is so important. Okay, now why is this happening? You can also write that down.
Sir, can you scroll up to the element electron transition? I need to add the groups of
Yes,
series.
please write it down.
Do you also have to add the part of the spectrum they correspond to, or that's not as non-essential?
It's not very essential. That's it.
Microwave or infrared, these ones.
It's just to show you that the higher jump they make, the higher frequency they have. Okay.
All right. Thank you.
Okay. Now, अब अगर पढ़ लो बेटा पढ़ लो मैच छोड़ दो okay when when potential difference is applied, the electrons of the gas gets excited as they absorb energy and do upward quantum jumps. All right. When they de-excite and move back to the ground state,
They give a photons based on the amount of levels they reach.
yes, they release photons according to the jumps they have made, like we did yesterday, right? For the wavelengths that we found. We let them pass a grating and a prism to diffract and then disperse, because grating would diffract them, prism would disperse them into colors. Okay, onto a screen. Now there are other wavelengths released as well, like infrared, microwave, and stuff like that, and even UV. But we only get to see, we get to see only visible light spectrum, because our eyes can only detect those. All right, better remember that. In fact, no matter what voltage or energy is supplied, we get the same result like that. So you can write this piece and let me know if there's something you want to ask. So then we'll go forward. While you're writing, I'll be back in like 2 minutes. All right, done. You guys have written it. Should I go forward, please?
Yes.
Okay, good. So next would be absorption spectra of hydrogen. Now we can do the opposite as well. It's called the absorption spectra of hydrogen. We'll do the experiment as well. First of all, we need a source of light, like a bulb or something. And obviously, that will have a filament. And this filament must be white hot. When it releases, we put a gas in front of it. So the white light is going through this gas. In this one, we have low pressure, low temperature, hydrogen gas. We want maximum number of electrons to be inside the ground state, okay? Already. So as the light passes, the electrons of the hydrogen are going to absorb the photons that they require. And when they do, they're going to release afterwards those back and we'll see the grading. When you see the grading is going to diffract them into a prism and from that prism basically we look at onto the screen what's happening. So interestingly, on the screen we see a pattern like this. We have all range of colors coming in. As you guys know, white light contains all colors.
And they're not discrete.
Sorry?
They're not. The lines won't be sharp.
They won't be sharp, they will be mixed. Okay? more mixed than what I'm making actually. Okay. You can keep on. If you don't want to draw this one, it's unnecessary. They're all colors in the white light, basically. So all these colors like rainbow is there. But then what we see here is bunch of discrete black lines. Some colors are missing. All right, kids?
And these black lines will have fixed positions. For example, one will be at light indigo, one will be at blue.
Yeah, the cyan one. Yeah, that's correct. Just like you've seen the previous one, you'll have their fixed positions. And these lines have the same wavelengths as what was emitted 410, 434, 486, and 650 nanometers. Why? Because these black lines correspond to those photons which were absorbed by the electrons so they could make an upward jump. Rest of them, they did not need those photons, so they let them go. Is it clear? So basically, it's like an invert thing of what we do here. Understood? Like that. So that one was an emission spectra, the colors that were emitted when it was de-excited, and this is an absorption spectra, which means the photons which were absorbed and rest were emitted or let go because they didn't need it. Understood? So they would correspond to the same wavelengths that the structure of hydrogen needs for upward or downward jumps. Is it clear? Now we can write about it. That this one, it is lot like continuous spectrum. However, it has few lines missing. A clear gas chamber containing low pressure gas is used. A white hot source of light is given to the gas. An electron in the gas absorbs or absorb only the photon corresponding to the quantum gaps. That corresponds to the unique quantized levels within the gas, right? So these photons at specific wavelengths are absorbed. Hence, black lines appear. Is it clear, you guys? All right, kids?
Understood.
All right. Now, you can write this down, then I'm going to go to the next. Just want to do the next thing. When you're done, let me know, okay? So I can go to the last thing. Just need 5 minutes of your time, probably extra today. All right, kids. Done. Now the next. So I'm just gonna go with a small summary here, just to tell you what we have done today, and then we are done with the chapter. So if you have a hot, white hot source of light, so it's emitting stuff onto a prism. So it's gonna give you a continuous spectra. All the rainbow colors actually. like these. And then if you have a hot cloud of gas which is already excited, when it passes through the prism, it will give you an emission line spectrum, which is like, fixed wavelengths of the photons that it emits. Alright, kids, like that. And if you have a source of light, and then cold gas, when it goes to the prism, it's just gonna give you black lines which were absorbed. Discrete black lines. Every gas has its own unique pattern, which is signature to the gas, which means that the quantum structure inside, the energy level structure, is different within each gas. Cannot be same ever. And this will give you absorption line spectra. So this is the gist of everything. Do you guys understand this now?
Yes.
Cool. And that would be all for quantum physics.
Okay, sir. Allah